In this section, definite integrals are used to find the arc length of a curve. We approximate an arc, a segment of a curve, by straight line segments whose lengths are given by the familiar distance formula. D equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. If you didn't know that, the distance formula is derived from the Pythagorean theorem. So here's the y-axis, here's the x-axis. If I'm finding the distance between 2 points, you can create a right triangle out of that. And this distance here is x2 minus x1. This distance here is y2 minus y1. And the distance between the 2 points is the length of the hypotenuse. So that's just the derivation of the distance formula. In this section, we will assume that the functions are continuously differentiable on the given intervals. This means that their graphs form a smooth curve. In the above images, on the left we have a continuous function y equals f of x, whose length we seek on the interval from a to b. On the right, a close-up view of a portion of the curve. We estimate the length L slice of each portion of the curve on a small interval of length delta x. We use the right triangle with legs parallel to the coordinate axes and hypotenuse connecting the endpoints of the slice. The length h of the hypotenuse approximates the length L slice of the curve between the two selected points. So here we're trying to find this arc length here, and we're going to approximate it by finding the length of the hypotenuse of this small right triangle that we create, where it has dimensions delta x and delta y. So we have here that L slice is approximately equal to h, which h is equal to the square root of delta x squared plus delta y squared. What we're going to do from here is we're going to factor out delta x squared from both of the terms underneath the square root. That's going to leave us with 1 plus delta y quantity squared over delta x quantity squared. And from here, because we have a product underneath the square root, we can split this up into two separate square roots. And I'm going to go ahead and combine that fraction like this. So I have delta y over delta x quantity squared. And then from here, we can simplify this by removing the square root and the squared. So from here, as delta x goes to 0, we should know from Calc 1 that delta y over delta x essentially becomes dy dx, which is equal to f prime of x. So as delta x goes to 0 and n goes off to infinity, we're increasing the number of subintervals. Then we have that L slice is approximately equal to the square root of 1 plus f prime of x quantity squared times delta x. From the previous page, if we take a Riemann sum of all of these slices and by letting n go to infinity, we arrive at the following fact. If f prime is continuous on the closed interval from a to b, then the length of the curve y equals f of x from x equals a to x equals b is given by the formula L equals the definite integral from a to b of the square root of 1 plus f prime of x squared dx. And then next to that, you have the same formula, just using Leibniz notation for our derivative. If a curve has the equation x equals g of y, and g prime of y is continuous on the closed interval from c to d, then the length of the curve x equals g of y from y equals c to y equals d is given by L equals the definite integral from c to d of the square root of 1 plus g prime of y squared dy. And again, we have a similar definition just using the Leibniz notation of our derivative. In both of these formulas, the second form that uses the Leibniz notation might be a little bit more helpful because we can use the mnemonic device, the differential is in the denominator. So for example, in this case, we are integrating with respect to x, and so we have dx, and then dx is in the denominator of our derivative notation there. Example 1 says find the arc length of the graph of y equals the natural log of cosine of x from x equals 0 to x equals pi over 4. The first thing that I'm going to do is I'm going to find dy dx. And so we have 1 over cosine of x. And then we need to use chain rule and multiply by the derivative of cosine. And that's going to end up simplifying to be negative tangent of x. From here, I'm going to square my derivative because that's what ends up going into our formula for arc length. So we have negative tangent of x quantity squared, which is going to end up equaling tangent squared x. From here, I'm going to go ahead and add 1 to this. So I've copied down the arc length formula, and so now we can start filling in values that we know. Our lower limit of integration is 0, our upper limit is pi over 4, and then we did all this work here to find the derivative squared plus 1, so I'm just going to go ahead and put that underneath the square root. And then we have dx. Now, if I use the Pythagorean identity, I can rewrite tangent squared x as secant squared. And then we can get rid of the square root by taking the square root of that. And so we get this. Now, the antiderivative of secant of x is the natural log of the absolute value of secant of x plus tangent of x. And we are evaluating this from x equals 0 to x equals pi over 4. So let's go ahead and plug those in. Okay, so let's go ahead and evaluate each of these things. Tangent of pi over 4 is equal to 1. Secant of 0 is equal to the reciprocal of cosine of 0, which is 1. Tangent of 0 is 0. And then secant of pi over 4 is the reciprocal of root 2 over 2, which is just root 2. So this is equal to the natural log of the absolute value of the square root of 2 plus 1 minus the natural log of 1, which ends up being 0. So here, this represents our final answer and the length of the curve between x equals 0 and x equals pi over 4. Example 2 says, find the arc length of the curve y equals x cubed over x plus 1 over 2x on the interval from 1/2 to 2. So let's start off by finding the derivative, dy dx. That's going to be equal to 3x squared over 6 minus 1/2 x to the negative 2 power. So let's reduce our fraction. We have 1/2 x squared. And actually, I'm going to factor out 1/2. So that's going to leave us with 1/2 x squared minus x to the negative 2, like that. Let's go ahead and square our derivative now. And if we square this quantity, we'll get 1/4 times x squared minus x to the negative 2 quantity squared. Now, I'm going to emphasize this because this is often something my students do. Please, 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 a plus b to the nth power is not equal to a to the nth power plus b to the nth power. We need to multiply or FOIL this out. So this is equal to 1/4. Maybe I'll use the box method over here. So we have x squared, x to the negative 2, x squared, x to the negative 2. This is negative. This is also negative. So if we multiply, we will get x to the 4th minus 2 plus x to the negative 4th. And now I'm going to go ahead and distribute in the 1/4. Now I'm going to go ahead and add 1 to the square of my derivative. So to this expression here, I'm adding 1, and that's only going to change the constant term. So I'm going to have 1/4 x to the 4th, and then negative 1/2 plus 1 would give me positive 1/2. And I'm actually going to factor out 1/4 from this. If I do so, we get x to the 4th plus 2 plus x to the negative 4th. It's helpful to recognize that this is going to factor into x squared plus x to the negative 2 power quantity squared. Okay, so let's start plugging this into our integral. So our square root here, because we're multiplying two things, we can split this up into the square root of 1/4 times the square root of x squared plus x to the negative 2 quantity squared. And that's going to be able to simplify as well. So here we're going to get the square root of 1/4 is 1/2, and I'm going to factor that outside of my integral. And then the square root and the exponent 2 will undo each other. And so our integrand will be left with x squared plus x to the negative 2 power dx. And from here, we can take the antiderivative by using the power rule for integrals. So we get 1/2 times x cubed over 3 minus 1 over x. And we're evaluating this from x equals 1/2 to x equals 2. I went ahead and plugged in our limits of integration, and we find that the arc length of this curve between x equals 1/2 and x equals 2 is 33 over 16, which is equal to 2.0625. And that completes this example.